Hey everyone, and welcome to this video. My name is Jan, I'm from TU Dortmund University, and in this talk I'm going to present you our work on MxTasks. As we all know, hardware is going to be more and more complex, and we have many cores, we have complex memory architectures, and there's a lot of beautiful work investigating how to utilize this hardware in a performant way. And most of this work is built upon an abstraction we know very well, and that is threads. So threads is a control flow abstraction that is used in most operating systems and in most programming languages, and much research focuses on how to get the most performance out of the system using threads. For example, some work introduced new synchronization primitives to make threads scale up very well, even when using many cores. Other work built data structures that avoid latches in general by using this tricky atomic instructions. Another way is using hardware-supported synchronization to make parallelism comfortable, so you don't have to worry about synchronization at all. But this is bound to specific hardware. And despite all these solutions scale very well, they are all tailor-made, right? They are all made for a specific scenario. And in many cases, it's hard to implement those data structures or to transform the kind of synchronization to other applications. Another area is to teach the hardware the pattern of how application accesses the memory by using prefetch instructions. But again, the implementation is shift to the developer and is very tricky to make prefetching work, right? You have to reorder your code, you have to access the memory in batches, and so on. So don't get me wrong, these are all great work, and there's much more great work out there, but we think that by extending this thread-based building, it becomes shakier and shakier. And at some point, you have to take down and rebuild to get rid of this in danger of collapsing architecture. And that is what we do with our task-based approach. In our work, we want to break up with this hard to implement thread-based abstractions, and we present our task-based solution that make developing of cache-friendly and parallel data structures significantly more simple without losing any performance. So let's see why we think that threads are not the best matching abstraction for data-intensive workloads. Threads are by design a relatively long-running set of instructions. During a thread, you have multiple memory accesses, and for the hardware, it's hard to predict which data will be accessed in the near future and which data will be read or written. And there's already some work going on that tries to profile and guess the intention of the next steps that a thread will do. But in general, there's no way to tell the operating system or the application or the execution layer the intention of the application. And it would be great if the application and the operating system or the hardware could work more closely together, right? And that's where we came up with the idea of tasks. In general, tasks are very small and close unit of work. So when implementing data structures, you have often some kind of closed job and you put them together in your large thread, right? When using tasks, you will have one task for each job. And we will see some examples later what I mean by closed job. In our vision, each task accesses only a single or at least a few data objects during execution. And then the entire job is not done by a single task. The task may spawn further tasks that continue the global job in fine granular steps. So the equivalent of executing long-running threads would be to fire multiple short-running tasks. That is what the figure here intends. And because tasks are that fine granular, it's very simple to pass a task's intention to the execution layer. Something like, hey, execution layer, this task will access that data object. I will dive into that mechanism later, But let me first give you an example of what I mean by fine granularity. So the idea of task is not something that was newly thought up by us. To be honest, there are multiple similar concepts discussed in different communities. Fibers, for example, are some kind of user-level threads in Windows. Another example is the Intel TBB library, which uses tasks to balance the load on the user level. And the new C++ coroutines are also some kind of tasks. Our MxTasks, as I said before, are designed to be very fine granular. A great example to typify is some kind of a tree structure. So think about how you would implement traversing the tree with threads. You would use a loop that iterates over the nodes, one after the other, starting at the root node, until you find a leaf node. Using the task concept, you spawn a new task for every single node you visit during traversal. So we start by spawning a task that accesses the root node. The task finds out which node is the next within traversal, and then it spawns a new task for that node. Again, the task examines the next node to access, and then it spawns a new task for that node. Here, the last task in this chain of tasks will now visit a leaf node and performs some action. For example, it inserts a new record or something like that. Okay, with that vision of fine granular tasks in mind, let's see how tasks can help the execution layer to better understand the intention of the application running on top. So what we see here is the tree from the last side on the right and the code of a task that inserts a record into the tree on the left. And imagine if you want to implement an insert operation based on threads, you would have a big loop that fetches one node after the other. And this code for this task is very similar. But in contrast of a big loop, you will spawn a new task for every node. And this is what we see here. When the task finds the next node to visit during traversal, it spawns a new task for that node. And we do this multiple times until spawn a task for the leaf node that performs the insert operation. So what are the benefits of tasks instead of threads? The strongest point is that we know the access characteristics of tasks when we spawn a task and not at time when executing that task. For example, in this scenario, we know the data a task will access because we spawn a task for a specific node. Another example is that we know the access pattern of the task. For example, will the task read or write to that data? In this case, the task will read nodes during traversal and write just to the leaf node. And when we know the next node is just an inner node, we also know that the access will be read-only. So the unique point of our MxTasks is that you can annotate such knowledge in form of metadata. In other words, you can transfer knowledge from the application level to the execution layer by writing such information to a specific task. For example, this task will access that node in read-only mode. Before we see how MxTasking uses these information, let's see what information we can attach to tasks. There are many things we learn from threads, like you can annotate the priority a task will run with. You can also force a task to run in a specific core or in a specific number region. But the most important annotation is this relation of data objects and tasks. So you can annotate the task with a specific data object the task will access during execution, like the tree node we just saw before. And you can also annotate the access pattern, like this task will just read that tree node. Okay, so the one side is to annotate your task with knowledge you have from the application. The other side is to annotate data objects too. You can desire your object to be placed in a specific number region. You can tell the execution layer in what way the object will be accessed by tasks. For example, is it accessed very often or just a few times? Think about the tree example. The root node will be accessed fairly often, but the leaf nodes will be accessed just a few times. And a very useful annotation we'll talk about next is this isolation level annotation. You can desire in what isolation tasks will access an object. Should every task be every access be exclusive, or do you allow reads in parallel? And from this, you can imagine what we can do with this metadata. We can move the synchronization from the application level to the execution layer to simplify the development of parallel data structures. Let's dive into that. So again, here is the example with a task-based tree implementation, but we have now added a new line to the task code, and this is the annotate function call. The annotate function lets you annotate the task with two information. The first is the data object a task will access during execution. The second is if it will read or write that object. And as the next node is an inner node and we are traversing that tree, we know that the task will only read that node. After the next execution, we know that the following node is a leaf node. So we can say, okay, the next task will write to that node. And that is what we annotated here. And the leaf node will just insert the record. So far, we just annotated the information, but how can we use it? Let's see how we execute that task. To be honest, there's no magic in our task execution. It's just a simple loop that gets the next task from a pool of tasks. And every time you spawn a new task, it will be pushed to that pool. And every time we want to execute a task, we pull the first one from that pool. So using the metadata we annotated to that task, we can now move the synchronization from the application layer to the execution layer. You may have seen these latch calls around the node axis. And before we read or write to a node, we have to take the latch first. Now, when we know which node a task will access, we can just wrap the latch code around the execution. And for the developer, this is a big win because she has not to worry about synchronization, which is very tricky and error prone. And instead, you only have to annotate your tasks with data objects. And if we extend this idea, there's another very useful annotation the developer made, and that is this read or write annotation. When using it, we could, for example, change the simple spin lock to a reader writer lock, which allows parallel reads at the same time. But we are not bound to a specific primitive. We can choose from a set of different primitives. And this is what MxTasking does. It takes the annotations at runtime and decides which is the best matching synchronization primitive for a specific data object. That could be a spin lock or some kind of optimistic version lock. It depends on the situation and the desired isolation level. And as a result, the developer has not to deal with synchronization. Instead, she can focus on implementing the application and let MxTasking do the rest. So this is one very strong benefit you get for free by using tasks. And there's another one I will show you next. When you remember the first slide, I mentioned that to make prefetching work, you have to adapt your application's code by accessing data in groups or something like that. So what is the problem here? Every time the CPU accesses data that is not cached, it has to wait until the data is loaded into the cache. And at this point, we can benefit from the relationship between tasks and data. Because we made this annotation, the tasking engine knows which data is accessed by which task. And by using this information, it is very easy for the engine to load data into the caches because it knows which data is accessed when. Let's see how it works. What you can see here is the task pool I mentioned this slide before, and the worker that executes the tasks. And every time we spawn a new task, we also analyze the annotations. And we fill up a separate buffer with information which data is needed by the task. That is the descriptor of the task, because that's where parameters for the execution are stored, and the descriptor of the access data. We do that for every task that is spawned by the application, and now the worker begins with execution. But before executing the next task from the task pool, it takes a look into the prefetch buffer and instructs the memory subsystem to prefetch the data for the task that will be executed after the next. So we will execute task 0, but before the worker starts prefetching the data of task 1. And while executing task 0, the memory subsystem loads the data for the task 1 into the cache. And ideally, the prefetch is done at the time the execution of the current task ends. And now the next task finds the data ready in the cache. And again, before we start executing task 1 here, we will first start the prefetch for task 2. This kind of prefetching has two benefits. The first one is you do not have to change your code. The only thing you have to do is annotating the task with the access data, but this is very trivial to make, right? The second benefit is this will work across different task-based applications. When you use prefetching in a thread-based world, the operating system may suspend your thread or something like that, and your prefetch may be misplaced. This cannot happen in our task-based world. Okay, let's see if this extra effort of task is paying off in terms of performance. What we see here is a task-based billing tree implementation. That is the green line, compared to a billing tree implementation of threads, that is the blue line, and one implementation using Intel TBB, that is the red line. And there are also some state-of-the-art data structures. As a benchmark, we use the YCSB with 3 different workloads. The first plot is an insert only, so we just fill the tree with 100 million key value pairs. The second one is mixed with read and update operations, and the third is a read only, so we have just lookups here. On the y-axis, we show the throughput, so the higher the better. What we can take away from this result is that our MxTasks has no significant more overhead, right? Its performance is at least the same as the thread-based implementation, but especially in the read-only workload, we benefit from prefetching and achieve around 25% more throughput than with threads. And keep in mind that the effort of the developer is significantly less, and it still achieves similar and better performance. So let me wrap up for you. We have seen that the combination of fine granular tasks and annotations make parallelism and prefetching very easy. You do not have to worry about synchronization or prefetching. You just have to annotate your tasks, and MxTasking will do the rest. In terms of performance, we saw that there's no significant overhead for tasks, and we benefit from this prefetching for free. To give a look ahead, the MxTasking is one building block of our larger MX kernel effort. The MX kernel is a bare metal platform. You can see it in the figure here. And it runs directly on the hardware and enables both the operating system on the one side and the database on the other side to run on top. With that, we envision to bring the database and the operating system more closely together instead of fighting each other. This is what we see today. So thank you for watching. And if you have any question, feel free to contact me.